In this video, I'll cover a utility class in Java, the math class. You can think about the math class as your calculator. It has functions you'd find on a basic calculator as well as a few scientific methods. I'm just going to cover the basics in this video. Back in one of the first sections of this course, I showed you examples of numeric overflow and underflow. This happens when an operation on a value causes it to exceed the maximum or minimum values allowed for its declared type. Let's look at that again, this time in more detail. I've created a new project called MathRandom Project with the usual main class and main method in the dev.lpa package. I'll start with a local variable called max-5 and set that to the integer's max value -5, so it's only 5 integers away from an overflow situation. I'm going to set up a for loop that will cause an integer overflow. I'll add 2 variables in the loop initialization code, id, which will represent a variable I might be using for an id, and j as the loop counter. I'll initialize j to 0 and id to the max-5 variable. I only want to loop 10 times to show you what happens with the id variable as I increment it past the integer's maximum value. I'll break out of the loop after 10 iterations, incrementing both id and j with each iteration. I'll print out id using a format specifier to print this number with commas so it'll be easier to read. Running this code, I want you to see that an overflow happened. It's a kind of silent overflow because the code just kept working. My IDs turned negative after the 6th iteration, which could be a pretty bad thing if you were relying on the numbers to increment normally. In cases where there's a chance you'll overflow, Java offers a series of methods on math which will throw an exception if the value overflows or underflows. I can replace the post increment operator on the ID variable with a call to one of those methods, which I'll do here. I'll call math.incrementExact, passing it ID. I have to reassign the result of this method to the ID variable. Now, if I run this code, I get an arithmetic exception, integer overflow. Would you want to use math.incrementExact in every for loop? Probably not, but in cases where an overflow would be a big problem, throwing an exception and having other code handle that exception may be better than allowing numbers to go negative if that's not behaviour you expected. I'm going to comment out this code for now. There are also methods named decrementExact, addExact, subtractExact, and a couple of others that can be used if you want to catch an overflow situation. You probably know what the method ABS is for, getting an absolute value of a number, which returns the magnitude of a number, ignoring its sign. Here I'll just print the result of calling math.abs on -50. Running this prints out 50. Now let's consider what happens if I pass in integer's min value to this call. I'll copy and paste that last line, and I'll change -50, putting integer.min value there instead. Running this code now to see what we get. You might be surprised that I actually get a negative number, the value of integer.min value. Calling this method on that value caused an integer overflow. If I wanted the absolute value of integer.min value, I could use ABS exact. I'll copy that last line and paste it below and change ABS to ABS exact. Now if I run this code, I get an exception. That might be okay, but I'd have to code for an exception to handle this situation, and maybe I just really want the absolute value of this number. I'll comment that last line out. I'll paste the code from the line above again. I'll use a cast now to along as I pass this parameter. This calls the overloaded version of the absolute method that takes longs. If I run this, I'll now get the absolute value of integer's min underscore value. 2 methods you'll probably be using a lot are 2 I've already used previously in method references. IntelliJ will prompt you to replace any ternary operations you set up to return a minimum or maximum value, replacing that code with a method reference. These only take 2 arguments and will return either the min or max. There are 4 overloaded versions for each that lets you pass an int, long, float, or double. I will just show you a couple of quick examples. For the first, I'll do something simple and compare 10 and -10 using math.max. Hopefully there's no surprise here and the output is max equals 10. I'll use doubles for the min method next. I'll pass 2 decimal numbers that are pretty close to each other. Running this, I get min equals 10 point followed by 6 zeros and a 2. Now let me just show you what happens if I make both of these floats by adding the f suffix to both. If I run this, I now get min equals 10.0. The float values aren't precise enough to maintain the least significant digit, the number 2 in this case. If I make that first argument a double by removing the suffix and run it, let's see what happens. I get the same result as previously because the double version of min is used if either of the arguments is a double. Hopefully you remember that a literal decimal number is a double by default in Java. Okay, so let's move on to a few more interesting methods you might find useful. I want to look at round next. This method takes either a double or a float and will round down to a whole number if the decimal part is below 0.5, otherwise it rounds up. If the arguments are doubles, a long will be returned, otherwise an int will be returned. I'll add a couple of tests. First, I'll confirm that if I pass 10.2, I'll be rounding down to 10. Next, I'll make sure 10.8 is rounded up to 11. Finally, let's see what happens if I pass 10.5, running this code. The output shows round down equals 10, round up equals 11. Round question mark also gives me 11, so the decimal part of the number needs to be 10.5 or greater to round up. If you don't want things to round up, you'd use the floor method instead. Likewise, if you don't want things to round down, you'd use ceil, short for ceiling. These methods return a double. I'll demonstrate floor using 10.8 and ceil for 10.2, running this. For the math.floor method, you can see that it doesn't matter how close the decimal brings the value to a whole number, it will always round down. For ceiling, it will always round up. Let's look at two more methods that are commonly used. First, there's square root or math.sqrt, and I'll pass that 100. Next is math.pow, which is raising a number to a certain power, so 2 to the third power is really 2 times 2 times 2. And I'll show you another 10 to the fifth power. Running this code, you can see the square root of 100 equals 10, 2 to the third power is 8, and 10 to the fifth power is 100,000. Notice that both of these methods return a decimal number or a double. I won't belabour these methods further, but there are methods available for algebra and trigonometry if you need them. This class also has the constant definition of pi if you're doing geometric calculations. Let's look at one last one, and that's math.random. To demonstrate this method, I'll call it in a for loop 10 times. I'll print out what I get from calling math.random. Running this code, I get 10 random numbers, all between the numbers 0 and 1, including 0 but not 1. That's interesting, but you might be asking why would you use this when you can just use the random class? That's a good question. I'll answer that question in the next video when I talk about different methods to randomize values. I'm going to end this video here on the math class. I'll see you in the next video.